Hello everyone, today we're back for some number theory, finally. I know it's been a while since we've done any of these, but here we go. So the first problem I will say is like a really difficult one, especially in terms of understanding the problem statement itself. Because look at this. If 2 to the 8th plus 2 to the b is equal to 3 to the c plus 3 to the d, the number of integers a, b, c, d which can possibly be negative is at most what? So like when I first read this problem, I interpret it as like ABCD, the number of integers ABCD which can possibly be negative, means that we're trying to find how many quadruplets ABCD satisfy this equation, and this is just clarifying that they can possibly be negative. So that took me like forever to figure out. And then I asked ChatGPT, and then it told me that this means that we're being asked how many of these integers can possibly be negative, which like the grammar just doesn't make sense to me at all. But it's okay. It's just because this is a 1963 problem. So I hope AMC has that problem fixed now. But anyways, yeah. So for this problem, it's pretty difficult, and I didn't really understand how to do it myself if I didn't have the solution, but I did understand the solution. So I'm just gonna use this solution to explain this to y'all. And I'll just like kind of add some interpretations along with reading the solution. So first of all, we basically try to case work this and then prove how many of the cases can work. So the first case is when C and D is greater than or equal to 0, and then A and B can possibly be less than or equal to 0. The second case is when A and B is greater than or equal to 0, and C and D can possibly either one or both be less than or equal to 0. Less than 0. And then finally, when A and C, or D and B, obviously, because A and B and C and D are interchangeable. So when A and C is less than 0, and and the other ones are not, B and D. So now we have to prove like how many of these situations work. So first of all, since A is less than 0, that means the exponent is negative. So we have the power on the bottom of the fraction. So if we do the negative of A, then now we will have positive fractions. So now we can multiply both sides by 2 to the negative A. Obviously, this one becomes 1. This one becomes, that part's obvious. But now we prove, actually the proof that we use for all three situations are rather similar. We use modular arithmetics, modular equivalence. I'm not that good at number theory, but basically we find the mod of all three equations and then prove whether it's possible. So the first one is not possible, obviously, because, well, if A is equal to B, then the right side is even, obviously, well, left side is odd. And when A is not equal to B, there's non-negative like the equation does not, no, I'm sorry. When A is indeed equal to B, there is no value of C and D that satisfy the equation, because 3 to the C plus 3 to the D has to be 1. That's not possible. So the first situation is impossible because of different modulos we get. So that's the situation when A is possibly less than 0. So now we assume that A and B is greater than or equal to 0. However, C and D, 1 or more, can be less than 0. So now we basically have this situation. So this is like, I guess, a general trick you'll want to do with number theory problems, is like putting it in this form, 1 over 3 to the negative C, instead of just 3 to the C, because C is negative, but it doesn't matter. We multiply both sides by 3 to the negative C, just like last problem, and this time we don't even have the case work, because it is obvious that the left side is indeed divisible by 3, because C is negative. So 3 to the negative C is going to be a positive exponent of 3, so that is going to be divisible by 3. However, the right side is obviously not divisible by 3, because D minus C is positive, as we assumed above, and so the right part is going to be a multiple of 3. However, we added that by 1, so it's not going to be a multiple of 3, so these two cannot possibly be congruent. And now that leaves us with the last case of A and C is less than 0, and B and D can also be negative, but they don't have to be. So this time we use the exact same trick, in which we pull the fraction onto the denominator and negative them, and then we multiply both sides, however, this time by A to the negative A times 3 to the negative C, and then we get this thing for Bobby. So this makes both sides integers, obviously, because the negative of a negative exponent makes it a positive exponent. And the right side is congruent to 0 modulo 3. Left side, obviously, because this is positive, and 3 to the negative C is going to be definitely a multiple of C. However, the right side can be either 1 or 2, obviously. So yeah, because the 2 to the negative A, which is a positive multiple of 2, cannot divide 3, and 1 plus 3 to the d minus c, in which because d is greater than c, it's going to be not a multiple of 3 either, so the right side does not divide 3. However, the left side does, so this is not possible. That means neither a, b, c, nor d can be negative, and that leaves us with the answer E, in which 0 of these 4 can possibly be negative. So yeah, this is a pretty difficult problem, and I would say like understanding the problem statement is also a difficult part. And also just knowing the trick of pulling the exponent to the denominator and then making it negative, so we don't have to actually deal with fractions and negative exponents. And we can just use modular arithmetics when it's integers. Okay, now let's take a look at the second problem. The second problem is way easier than the first one. So for any positive integer, the number of prime positive integer greater than 1, we're trying to find the number of primes that's between n factorial plus 1 and m factorial plus n. Literally, if you know the definition of prime numbers, that means this number cannot be distributed into multiples of 2 numbers that are not 1 and itself. And you can easily realize that all of these numbers satisfy that constraint, because n factorial, okay, let's just say this number is in the form of n factorial plus x. We know x is between 1 and n. That means we can just factor out an x in this addition, because n factorial is going to have x as its factors for sure, because x is between 1 and n. That means none of them are prime. 0. Yep. Okay, so that is it for intermediate number theory problems review today, and just a little bit of recap on how I've been doing grinding for aime. I think I'm just kind of cooked for the aime this year and maybe next year, because today I did 3 combinatorics problem and it took me like 1.5 hours. Not great at all, but my friend also recommended me a site of AMC Trivial, so maybe I'll start doing that. I don't know if it will help. Hope it does. Thank you for watching this video, and I'll try to make a video again tomorrow and see if I can actually get some hours in. Like last winter break, 10.5 hours a day of use ago. I want 10.5 hours a day of math.